So in the last lecture, we did Kelvin-Helmholtz instability, right? And that was a type of hydrodynamic instability. So there we were talking about how the velocity in the fluid, which in particular the shear flow in two-layered fluid or stratified fluid creates instability, right? Where instability was in form of wave, and then slowly wave overturns and that brings mixing, etc. So that was a purely a type of hydrodynamic stability, whereas in today's lecture we are going to do Rayleigh-Benard type instability, which is also known as thermal instability. Okay, so what exactly happens in this case is we start with Rayleigh-Benard instability, but then we will also consider other type of convection. So Rayleigh-Benard instability is particularly is meant for heat transfer in a fluid between two parallel plates, okay, two solid plates. So here let's assume that this is a solid body, right, which is, we also call it rigid boundary, and this is also a type of rigid boundary. So these are two solid surfaces, and in between we have a fluid of density, let's say rho, and different thermal properties. Okay, and we start heating the lower part with temperature that is delta T greater than the upper layer, right? Upper layer is kept cold and lower layer is made warm. Okay, so when we heat it up with temperature of delta T compared to the upper layer, slowly heat transfer begins, right? Heat flux goes from bottom layer to the upper layer, and originally heat transfer happens in form of thermal conduction, right? And there is no movement of fluid. But what happens when you continuously heat it, or if you increase the value of delta T, so the temperature difference becomes significant that it starts moving the fluid molecules. So originally the heat transfer is happening only in form of conduction, but slowly when these fluid molecules or fluid parcels, they become buoyant, they starts moving up themselves, right? They starts rising up. And why? Because they have got buoyancy force which has become greater than the viscous force in the fluid, right? So initially there is high viscous force, and that does not let this buoyant fluid to rise up, and that's why heat transfer only happens initially in form of conduction, right? But as you increase the temperature or time increases, the buoyancy force in the fluid parcels actually starts increasing, and that becomes greater than the viscous force, and that is the moment when the convection begins. Okay, and so that is why in this particular case the viscous force actually works as a stabilizing effect, so it keeps the fluid stable, whereas the buoyancy force actually makes the system unstable. Okay, and that's why this brings destabilizing effect in the system, right? And why the system becomes unstable when you start heating up? Because these particular fluid parcels, they are now lighter, right? Their density decreases compared to the ambient fluid, and now because they have got lower density, they cannot stay at the bottom under the heavier density at the top, right? And that is why the system becomes unstable and convection begins, right? And when the convection has just begun, it happens in a particular pattern. It does not happen very randomly. Okay, and something is shown here in this simulation which was performed by this particular author. So here you can see this hot fluid actually starts rising up at this particular location, right? Likewise, Heavier fluid from the top actually comes down at these locations. Okay, so in the beginning actually it maintains a fixed pattern which you may call it to be a wave. Okay, so it looks like a wave, and it has an amplitude, the amplitude as well as the wavelength. So here let's say this is your wavelength, which will give us the wave number as 2 pi by lambda, where lambda is the wavelength and k is the wave number. So this is something we already discussed in case of hydrodynamic instability or Helmholtz instability. So similar kind of thing also happens in case of thermal instability. So when convection begins, it begins in a fixed pattern, particular pattern, where you will have this hot fluid rising up, and just beside it cold fluid from the top will be coming down, and that is why it looks like a wave with crest and trough, and that's why we can define wavelength, wave number, etc. Okay, and depending on your conditions, like if you increase the temperature further, you might get a different kind of wave behavior like this, but this actually always starts in a particular pattern. And here are also some experimental images. So what you see here in the upper side, these are numerical results, but what you see here is the experimental image. Okay, so this is taken from the top, while these ones are the side view of a convection, or the pattern in which convection begins. What you see here is the top view. Okay, and you can see it actually starts in this particular case, it is showing in a hexagonal shape, right? And in this actually for this particular condition which has been is under consideration here, the convection everywhere begins in this particular shape, and it follows more like a wave type behavior because it has a fixed pattern, right? So this can be defined as convection happening in a fixed pattern, right? And this is for a particular case where we assume that there are solid surfaces, and fluid is actually, there is a convection happening from bottom to top and top to bottom, right? And in this case it is assumed that the horizontal length scale is like infinity. So we are not really considering how wide it is horizontally. We are only worried about how thick or what is the gap between these two surfaces. Okay, so this experiment that is performed is by Benard himself. Benard and theoretical analysis by Rayleigh. Okay, and that is why together this convection is known as Rayleigh-Benard convection, okay, which happens between two parallel plates which is filled with a particular type of fluid. Okay, and so this was very first time analyzed by Benard experimentally, and few years later this was theoretically analyzed by Rayleigh. Okay, and today also we are going to analyze this particular case along with a few other cases. Okay, so for theoretical analysis, we obviously start with this set of equations which we have considered before. So one of them is obviously the continuity equation, and then we have Navier-Stokes equations. In this case we also consider the heat equation because there is heat transfer from the bottom plate to the upper plate, and then linearization and normal mode analysis etc. are done with perturbation. So the analysis here is obviously much more complicated than what we should be doing here, and that's why I'm not showing complete analysis. We are only going to talk about the critical numbers or behavior of convection depending on different dimensionless numbers. Okay, so the result that is obtained for Rayleigh-Benard convection is shown here. So here you see there is this K, which I will call K hat, and here is RA. Okay, so K hat, here is the dimensionless wave number, or in other words, this is actually defined as KH. Okay, where K is the wave number and H is the gap between the plates. Okay, and you also see sigma here, that is mentioned. Sigma is smaller than 0. This line belongs to sigma equal to 0. In here sigma is greater than 0. So this sigma is basically equal to omega that we discussed in case of waves, and that is the frequency, okay, which is used for the normal mode analysis. And if sigma is smaller than 0, then the system is stable. In that case, heat transfer happens only through conduction, and if sigma is greater than 0, then heat transfer happens through convection. Okay, and what you see here is in form of RA is the Rayleigh number. Okay, which is given as, okay, we can discuss that in the next slide, but RA is defined as buoyancy force over viscous force. Okay, and we'll discuss its formula and the number. So what do you see here is when, so analysis is based is done based on the sigma value. In this zone, when you see, when it says stable, this is basically the conduction zone, right? So when sigma is smaller than 0, heat transfer happens only in form of conduction and there is no fluid motion. Okay, but what you see in this case, this is the unstable case. This is basically the convection zone, right, where fluid flow occurs. Okay, and here you will see that it follows a particular curve, and the Rayleigh number that we have, the critical Rayleigh number that separates conduction from convection, or the moment where instability begins, right, that depends on the K hat value, right? And so for each place you will see different K hat value for different RA value, but in this curve the minimum Rayleigh number we get is at this point, that is 1708, and that is for K hat of this. So that is the minimum critical wave number, dimensionless wave number, and minimum critical Rayleigh number. Okay, so we will analyze that little further now. So here Rayleigh number is actually defined as gamma G delta T H cube over alpha nu. Okay, and this is something we have done before also, where gamma here is thermal expansion coefficient, G is obviously the gravity, delta T is the temperature difference, h here is the length scale, which in current case is the gap between those two parallel plates. Alpha is the thermal diffusivity and nu is the kinematic viscosity. Okay, so these are different terms, and this is how Rayleigh number is defined, which we already discussed what it is. And the critical Rayleigh number that we get here is, I'll call it Ra critical, is 1708 for Benard convection. For K hat critical equal to 3.12. Okay, so these are the minimum value that we have beyond which convection should begin. But we need to notice that this K hat critical or K hat can depend on the flow conditions or several different conditions. So depending on what kind of pattern we are generating, like here we have seen this hexagonal pattern, but not necessarily there will be hexagonal pattern in all cases, right? So depending on what kind of pattern we get in convection, your critical Rayleigh number might change depending on the wave number of the pattern that we get. Okay, and that is why this critical Rayleigh number that we get as 1700 is the minimum critical Rayleigh number, but there might be other values of Rayleigh number depending on this curve that we have seen. Okay, so this value that we see is for Benard convection, both these value, which actually means that top and bottom surfaces are rigid, right? They are basically solid borders. Okay, but then there are other cases where for example, let's call it case 1, right? That is the Benard convection. We can now think about another case when we have only the bottom part is a rigid boundary. Okay, and we have fluid and upper surface is open. Okay, so this is a this can be called as the free boundary. Okay, where we do not have any sort of effects from the top. In this case, obviously again we assume that we are heating from below, okay, with a temperature of delta T, that is the difference between the temperature of heating versus the fluid temperature. And here the Rayleigh number we get, Ra critical, is roughly 1100 for K hat critical of 2.68. So this is when the upper part has free boundary and the lower part is rigid. Okay, that is case 2, whereas in case 1 both are rigid. Now we can also consider case 3, where we assume that, let's consider this is the solid boundary which is there, and then this is filled with some sort of fluid, but then there is another layer of fluid. Okay, where if this is row 1 and here it is row 2, where row 2 is much greater than row 1, so convection in uh, row 1 may not affect convection in row 2. So for row 1, this is a free boundary, this is a boundary, and also this part here is a free boundary. Okay, so if we have one fluid on top of another, provided that your lower layer fluid is much heavier than the upper layer fluid, so that convection in upper layer does not affect what in the lower does not affect the behavior of lower layer fluid much. Okay, in that case, Ra critical we get is roughly 658 for K hat critical of pi over root 2. Okay, so these are all theoretical results, and they have been verified experimentally for different conditions. Okay, so this is how a critical Rayleigh number is found for different conditions, and here we are just considering these 3 different cases, but now there could be hundreds of different scenarios where Rayleigh number will vary depending on the geometry, depending on the flow conditions, and depending on many other parameters. And this has in fact been a very extensively studied topic in mathematics, or those who work on fluid dynamics or heat transfer. There have been thousands of researchers across the world who have worked on these problems to find Rayleigh number, critical Rayleigh number for different conditions. Okay, so that is what we have seen, but now let's see what actually happens when we increase the Rayleigh number, right? Or we have seen the critical Rayleigh number, and we now know that if the Rayleigh number for a particular heat transfer is smaller than Ra critical, then heat transfer happens through conduction only, right? That is, let's say, case 1, when Rayleigh number is smaller than Ra critical. That is something we have studied. Now when Rayleigh number of the heat transfer becomes greater than Ra critical, then instability sets in and convection begins. In a fixed pattern. Okay, and that fixed pattern can be considered as this example here, right? As we just discussed, the moment Rayleigh number becomes greater than Rayleigh number critical, it starts in a wave type form, where we can very easily define wave number or wavelength and frequency, etc. But now if you increase Rayleigh number further, that is case 3, let's say, that is much greater than Ra critical. In that case, the flow becomes convection is turbulent in nature, and no fixed pattern is found. Okay, so that is shown here in this example, case 3. So this is for Rayleigh number of almost 10 to the power 13, which is extremely large, right? And in the beginning, obviously, it starts with some perturbation, but you can see there is no such fixed pattern. Like if you see anywhere, for example here, that is very different from how it looks like here, how it looks here. This is very different. Likewise, for this case, you can see that is different. this is different from how you'll see here. So there is no such fixed pattern when Rayleigh number is extremely large, and eventually as we go from this to this to this at later time, it has become highly turbulent. You can see there is no fixed pattern and heat transfer is happening in form of a highly turbulent flow. Okay, so that is the case, and in fact in majority of cases Rayleigh number is extremely large, because you will see the formula for Rayleigh number is that Ra is proportional to h cube, right, where h cube, water, if you consider some length scale, it becomes extremely large, because length scale is something that we consider in range of several meters or maybe 100 meters as well, right, whereas alpha and nu are generally very small, and that is why Ra in general for any convection is extremely large, and that's why in most of the fluid cases we see heat transfer happening in form of turbulent flow without much fixed patterns. Okay, so far we have seen how this thermal instability develops and that brings convection, and that is why we also need to discuss one topic very quickly, that how this thermal convection is different from plumes that we have studied before, right? In fact, plume is something that we studied in great detail. So the difference between these two is, here this is obviously an example of plume, and here we call it, this is thermal convection, where you see that there are these parcels, fluid parcels rising, which are basically warm air that is rising from the bottom, right? So plume actually is generated, from a single source, right, whereas this is convection here generates from a distributed source, right? So what is the difference? In this case we have this warm fluid rising up from here from one particular source, right, whereas in case of convection you can see the complete surface here is getting warmed up, and that is letting the air getting warmed up, and that air is actually rising from different places, right, and in this, that's why we call it a distributed source, because this is not happening from a fixed point. Okay, so that is one major difference. So plume is also a type of convection, but that is happening from one single point rather than from a surface area. Okay, and other thing is, in case of plume can develop both due to delta T as well as delta C, right? And what is delta C? That is the concentration difference, right? As we have discussed, this delta rho that we need can come from delta T or delta C. This is something we have discussed in detail. So for plume to develop, we need some density difference, and this density difference can come from either temperature difference between plume and the ambient, or concentration difference between the plume and the ambient, and not necessarily they have to have temperature difference. Whereas when we talk about thermal convection, which is the point of interest in this lecture, thermal convection can happen only due to delta T value. Okay, so thermal convection develops only due to delta T, right? That is the difference in temperature, right? So, and that is why we are studying these two topics separately. And now if you think about plume again, because it's rising from one single point like this, we considered how there is entrainment happening from sides, right? In this case, your transverse flow was very important, what is happening from the sides. But when it comes to convection, the transverse flow is not really important because this whole fluid layer is assumed to be rising up. So what happens at the sides are not really important. What happens in longitudinal direction is more important. Okay, and that is another difference between this convection from a distributed source versus convection from a single source. Okay, so in the next lecture we will see some examples of convection happening in nature, in atmosphere, in how we can use the concepts that we studied in this lecture to model the convection problem in atmospheric cases.